Hello students, welcome back to this lecture series of M.Sc. Part 1st Physics, Mathematical Methods in Physics. Okay, in the last few lectures we discussed about the power series and the complex sequence, and also we discussed the power series, that is radius of convergence. Okay, so we are going to solve problems on radius of convergence. Okay, so first example, the series find the series of convergence. The series is given summations n is equal to 0 to infinite a n z minus z naught power n. Find this thing is a power series, so you can it is also considered the power series, and this a n, this is a characterization coefficient, so a n is given is equal to summation over a n is 5k plus 1 divided by 3k plus 1. Okay, it is power n. Okay, so and also the z naught is given, this z naught where we expand the power series around this z naught, so this z naught is equal to 3 item. Okay, so here I am using the ratio test. In the last lecture I introduced about the ratio test, but here I am using the root test. Okay, not ratio test. So root test, definition of the root test, that is limit L is equal to limit n tends to infinite mod k under root n. So if this L is greater than 1, less than 1, or equal to L, then we can find out the series is convergent or not. Okay, so just I am using this root test. This is root test. Okay, this using this root test. So for this characteristic coefficients, that is ak, if I apply the root test, I am not using here the ratio test, because if find the a n plus 1, then it is difficult to cancel out. Okay, our root test is like this, a n plus 1 divided by a n. So if I find a n plus 1 divide and the a n, so this is a n and n plus 1, this here is n. So this n become by n plus 1, so it is difficult to cancel out. So that's why we are using this root test. Okay. So L is equal to limit n tends to infinite, it is 5n plus 1 divided by 3n plus 1. Okay, so we can take out the common n, so it is limit 5 plus 1 by n, 3 plus 1 by n. Okay, so after applying the limits, we are having the L value of the L, that is 5 by 3. Okay, now the from the radius of convergence, we know the R is equal to 1 by L, and these things R is equal to, we can write 3 by 5. Okay, so this is value for the R. Now if I draw the regions where these things is expand, this series is expand, so here z naught is given 3. Okay. So here I am consider the 3 item, and here I am consider 3 iota, and this r is equal to 3 by 5. So around this in this regions we can expand this power series. Okay, so it is radius, it is 3 by 5. Okay, so this is about the radius of convergence. Find the series of convergence, radius of convergence. Okay, so this is about the radius of convergence. Now we are going to see the power series. Okay. Sorry, power series, Taylor series. So the Taylor series, in this Taylor series, if we consider the f of z functions, that is f of z is analytical, functions in region f functions f of z is analytical in region z minus z naught is less than r. Okay, this r is defined as some region or the domains. So this function is analytical in these regions, and also if z naught or z 1 and the series f of z is represented as power series and expand in circle where we consider the circle inside this interior R. Okay, so there is a circle CR I am consider, or the loop CR which is radius is less than R. Okay, so f of z is analytical in the regions z minus z naught is less than R, and f of z is represented as a power series and expand in the circle. So this f of z is f of z is converge in this circle where we consider the r is less than small r is less than capital R. Okay, so this things is called the Taylor series. Now if I consider the theorem of this Taylor series, and then we are going to prove this. So if functions, that is f of z is analytical in the region R, and we express is a power series, and that is convergent in the region CR. So this series is called the analytical region. Okay, now the theorem, if we see, so this theorem of functions. Okay, so first we are going to prove this. See the definition of the functions. F of z, that is analytical inside a circle z minus z naught is equal to R. This is region what we consider. Okay. So it is maybe as convergent. This is a statement of this theorem. So this f of z we can write f of z is equal to, or this series we can represent a power series in the summations, or n is equal to 0 to infinite a n z minus z power power n. Okay, and this a n is a characteristic coefficient. So this f of z, that is analytical inside the circle, this region we consider, and inside this region another region we consider, this circle. Okay, and in this circle one this power series, maybe it is convergent. Okay, so that we are going to prove, and this f of z is equal to, this is power series, and this an is a characteristic coefficient. So this an we can write an, it is f of n z naught divided by n factors. Okay, so this series become like this: f of z is equal to summation n is equal to 0 to infinite f power n z naught divided by n factors z minus z naught power n. Okay, right. So this is the statement of this theorem, Taylor series theorems. Okay, so we are now going to prove these theorems. Okay, so proof of this theorem, just you want these expressions, f of z is equal to these things. Okay, okay, so by using the Cauchy integral formula, we know the Cauchy integral formula. First I draw the diagrams. Here we consider so this is the regions, and here inside the region I am consider the one point, that is z naught, and in this domain or in these regions I am consider another circle. Okay, which radius is small r, and this regions, that is capital R. Okay, so here one arbitrary points I am consider, that is z. Okay, so inside this CR, okay, inside this CR, if I expand this power series, so this power series is converge in this regions CR. Okay, so if this z naught is the center, and this z is any arbitrary points I am consider. Okay, and this r is a small r is the radius of this CR. Okay, so here points I am consider, that is psi. Okay, on this CR. So by Cauchy integral formula, okay, or by using the Cauchy integral formula, f of z is equal to 1 by 2 pi I close integral over c, okay, into f of z divided by this is f of z naught, so z minus z naught dz. Okay, this is a statement for the Cauchy integral formula. Now for this case, if I write the formula by using this Cauchy integral formula, so from for this case we can write f of z is equal to, okay, so 1 by 2 pi I close integral over CR. So we expand inside this CR series. Okay, so that's why here is a close integral over CR, and f of psi. Okay, this point here I am point consider, that is a psi, and divide by psi minus z. Okay, psi minus z. So this arbitrary point I am consider, that is z, and into the psi. Okay, so here variable thing is what, psi. Okay, and so this is f of z. Now if I consider this psi minus in the denominator, what they we having the expression 1 by psi minus z. Okay, so if I consider 1 by psi minus z, okay, and this rewrite in term of the z naught. So just I am adding 1 divided by psi z minus z naught plus z naught. Okay, just two things, that is z naught, which is center of the CR, I am adding into this expressions, because z naught around the z naught we maybe we expand the power series. Okay, so for that I am just rewrite 1 by psi minus z naught z minus z naught. Okay, so if I am take out the common, that is 1 by psi minus z naught into 1 minus 1 divided by z minus z naught divided by psi minus z naught. Okay, so these things we can write 1 by psi minus z naught into 1 minus z minus z naught divided by psi minus z naught, just power minus 1. Okay, so this bracket we can expand by this bracket we can expand by binomial theorems. Okay, by using the binomial theorems, this bracket we can expand. So just I am right here, so it is equal to 1 by psi minus z naught 1 plus, if we expand, so 1 plus z minus z naught divided by psi minus z naught plus z minus z naught square divided by psi minus z naught square plus z minus z naught cube divided by psi minus z naught cube, and so on. Okay, you can find up to the n and then the n plus 1 like that. So this is after expanding this brackets by the using binomial theorems or binomial series, we are having these expressions. Now if I multiply what we are taking the common, that is psi 1 minus z naught, so it is like this: 1 by psi minus z naught plus, here is a square, here is a cube, and here is a 4, power 4. Okay, so this is the expression after multiplying this psi minus z naught to this series. Okay, so now if we this put into the formula, so we are in the formula, that is f of z naught is equal to 1 by 2 pi eta close CR f of psi divided by psi minus z into this side. Okay, so if I change this expression, is nothing but the 1 by psi minus z. Okay, so just I am replacing these things with this series. Okay, so if I put this first terms here, so it become like this: 1 by 2 pi eta close integral over CR, so f of psi divided by this, for the first term I am right psi minus z naught. Okay, so this is psi minus z naught, and this plus, if I write for the second term, okay, so this z minus z naught, here variable thing is what psi, so this term what are the numerators is this z minus z naught, it will be take out the common, so here z minus z naught divided by 2 pi eta close CR, close our integral over CR into f of psi psi minus z naught, here is a square. Okay, so that is square into this side. Okay, this is for the second term. Now if I write for the third terms, so it is 1 by 2 pi iota close CR. Sorry, here is also we can take out the common, that is z minus z naught, z minus z naught square divided by 2 pi iota close CR. So it is f of psi divided by psi minus z naught power 3, okay, bracket power 3, so into d psi and plus so on. Okay, so like this we can write for the same z minus z naught, okay, up to the power n. Okay. So this is after just putting the these things into this formula. So we are having this now series. Now by using the Cauchy integral formula for the nth derivatives, okay, Cauchy integral formula for nth derivative. Okay, so Cauchy integral formula for the nth derivative we know very well. So it is f of z n factorial, so f of power n z naught is equal to n factorial 2 by the close integral over c f of z divided by z minus z naught dz, and this z minus z naught power n plus 1. Okay, this is the formula. So we rewrite like this: f of power n z naught divided by n factorial is equal to 1 by 2 pi iota close integral over CR. Okay, so f of z divided by z minus z naught or n plus 1 dz. Okay, so for this case what we are consider, so this f of n z naughts divided by n factorials into these things we can change here. Here is a n plus 1 is as it is, here is only this function is psi, and here psi, and this is f of psi divided by psi minus z naught n plus 1 and dou psi. Okay, so these expressions if we replace with these things. Okay, now for the 1 by 2 pi I close integral over CR f of psi divided by z minus z naught d psi, here n is equal to what? N is equal to this n plus 1. Okay, so n is equal to obviously 0. Okay, in this case, so for the n is equal to 0, we can write this is f of z naught. Okay, here, and for second term, so that is z minus z naught divided by 2 pi iota close, here power is what? Psi minus z naught 2. Okay, so this n plus 1 is equal to 2, so it is n is equal to 1. So here this is the first order derivative of the f of z naught. Okay, so this n become 1 primes this is f primes z naught divided by 1 factorial and these things. Okay, and here is a 2, 1 plus 1 is equal to 2, and this expressions. Okay, now for this thing, if here is a power 3. Okay, so it is n plus 1 is equal to 3, so n is equal to 2. Okay, so we can write this n double primes for the second order derivative, okay, so here f double primes z naught divided by 2 factorial is equal to 1 by 2 pi close integral f of psi 1 minus z naught power 3 dou psi, and this is expression this one. Okay, this is, we take the common, that is z minus z naught. So just I am rewrite now by using this formula. Now, okay, so f of z is equal to, okay, so for these first terms, if I write, so it is f of z naught, okay, this expressions for the f of z naught. Okay, and for the second terms we can write this thing is common, that is z minus z naught. If I write, it is z minus z naught, and other remaining terms, that is these ones. Okay, so this is nothing but the f prime z naught divided by 1 factorial, so no need to write the 1 factorial, and plus for these terms I can write z minus z naught power or power 2 into, for this expressions we can write f double primes z naught divided by 2 factorial. Okay, so here is a power 3, so n is equal to 2. Okay, so from this f of n z naught, this n here is a 2 primes and n is equal to 2 factorial. Okay, and similarly I write for the next terms, that is z minus z naught power 3 f triple primes z naught divided by 3 factorial. Okay, so like this we can write up to the n z minus z naught power n f power n z naught divided by n factorial. Okay, also other term is presented, and that terms is called the remainder terms, so n plus 1. Okay, so this expression is called Taylor series. In this series we expand in the CR regions, and this series is convergent in this circle, CR circle. Okay, so if now one more points, if we consider this z naught is equal to 0, okay, so this series become a Maclaurin series. Okay, so this is a special case. So if I write series summations a n z minus z naught power k, or sorry n, and a n is a characterization coefficient, so it is a n summation over, so it is f power n z naught divided by n factorial. Okay, see I put here, so these things summation over f power n z naught is equal to 0 if I consider. Okay, in this case also if z naught if we consider the 0, so this become a z power 2, z power 3, like that. Okay, and this is f of z naught, so here 0 divided by n factorial, and this z minus z naught, this is 0, so this power n, and this series is called the Maclaurin series. Okay, so this is a special case for the Taylor series. Okay, okay, now let's take the one example on this Maclaurin series, sorry, on this Taylor series. Example is 1 by 3 minus z. Okay, this is a given series, and they ask the expand around this z is given equal to 2i. Okay, so around this point, sorry, z we want to expand this series. Okay, so same procedure if I follow what we are following the theorems. So this 3 minus, or this, okay, this 3 minus z we can write is z naught. Okay, so 3 minus z is equal to 3 minus z plus 2i minus 2i. Okay, just I am adding and subtracting this z naught. Okay, so this is 1 divided by 3 minus 2i minus z minus 2i. Okay, and this we can write, if we take out the commons, that is 3 minus 2i into 1 minus 1 divided by z minus 2i divided by 3 minus 2i. Okay. So this similar, if we expand by the binomial theorems, so this becomes like this, 1 minus divided by 2i into 1 plus z minus 2i divided by 3 minus 2i plus z minus 2i square divided by 3 minus 2i square, and so on. Okay, if I multiply, so this become these things, here is a square. Okay, multiply to this 3 minus 2i, so this is 1 by 3 minus z. Okay, so here if I using the radius of convergence, so this series is we can write summation over n is equal to 0 to infinite z minus 2i divided by 3 minus 2i, or it's k, and this thing is k plus 1. Okay, so this is equal to the power series. Okay. This is equal to the summations a n z minus z naught n. Oh, sorry, here is. Okay, so this is power series, so this is equal to the power series. So if you observe these expressions, z minus 2i, okay, so this z minus 2i is what? These things. Okay, z minus z naught, right? Z naught is equal to 2i. So, and the ans, this characteristic coefficient, we can write an is equal to summations over ans is equal to this in the denominator, so it is summations 1 by 3 minus 2i, that is n plus 1, like this. Okay, 2i n plus 1. Okay, okay, so this is characteristic coefficient. So now if I use the ratio test, that is L is equal to limit n approaching to infinite, so it is a k plus 1 divided by a k. Okay, so if I use this limit, and we can find the radius of this means we can find the regions where this power series we want to expand. Okay, so if I try to find the ak plus 1, so this is ak, or the ans, you can also write this is limit in the term of the, so here an, this is an. Okay, okay, so if I write an plus 1 is equal to 3 seconds, this is not k. Okay. So this is an, and if I write the an plus 1, so it is 1 divided by 3i n, sorry, 2i n plus 1. Okay, so if we are having the an plus 1 divided by an, so this, if I write from this two expressions, so it is a 1 mod 1 divided by 3 minus 2i. Okay, so if I solve this limit n approaching to infinite, 1 divided by 3 minus 2i. Okay, so if I simplify or multiply these things. Okay, this is an plus 1 and this is an. Okay, see, if I multiply, that is L is equal to limit n approaching to infinite 3 plus 2i divided by 3 minus 2i into 3 plus 2i, the mode. So I think this becomes limit 3 plus 2i divided by 13. Okay, 9 square plus 13. Okay, so and if I remove this mod, so it becomes 3 and the 13th. L is equal to 1 by 13th. Okay, 1 by under root 13th, and we know the R is equal to by the radius of convergence, so R is equal to 1 by L, so this R is equal to the root 13th. Okay, so this R is given, this is the regions where we want to expand this series. So if I draw, so Z naught is equal to 3i. Okay, so this Z naught is equal to 3i, and this radius, if I draw, okay, so in these regions, here the series is convergence 1 by Z naught. Okay, so this R is defined the regions, and this Z naught is the center of this regions. Okay, so this is about the Taylor series. Okay, so okay, so let's stop here.